So far, we've been converting AC into DC, but what if we want to create AC from DC? How can a simple battery or solar panel, which only gives rock-steady DC power, suddenly create the alternating current? Your fridge, fan, Wi-Fi router, and even radio waves need to work? No spinning generator, no wall socket. Just a tiny silent circuit doing the impossible. The answer is one of the cleverest inventions in electronics, the oscillator. And in the next few minutes, you'll see exactly how it turns flat, DC, into perfect, AC waves, and why this trick powers almost everything you touch right now. Let's start simply. An oscillator is a circuit that takes a DC power supply, a steady, flat voltage, and converts it into a continuously repeating AC signal. Think of it like a swing. You give it one push, that's your DC input. And then, if the conditions are right, it keeps swinging back and forth on its own. That back and forth motion, that's your oscillating signal. The signal it produces can be a smooth sine wave, a sharp square wave, or a jagged triangle wave, depending on the type of oscillator. But in all cases, the output is periodic. It repeats over and over, forever, as long as power is supplied. Now here's the question that every curious mind should be asking. If you start with a flat DC signal, where does the oscillation come from? How does the swing keep moving if nobody pushes it again? The answer is two words: positive feedback. But what does it actually mean? First of all, it creates a small signal, then feeds it back into itself, and after that amplifies it again and again. And just like that, a continuous wave is born. Imagine you're speaking into a microphone connected to a speaker. If the speaker is pointed directly at the microphone, that tiny sound gets amplified, fed back into the mic, amplified again, and within seconds, you hear that loud, ear-splitting screech. That is positive feedback in action. An oscillator works on a similar principle, but instead of noise, it creates a controlled, stable signal. Engineers call this the Barkhausen criterion. For a stable oscillation, the loop gain must equal exactly 1, and the total phase shift around the loop must be 0 or 360 degrees. Any more, and the signal grows out of control. Any less, and it dies out. And once you understand this, something really interesting happens. You realize there isn't just one way to achieve this balance. In fact, engineers have designed many different types of oscillators, each one built to satisfy this condition in its own unique way, and each suited for completely different applications. So let's explore the most important ones. First one, RC oscillator. RC oscillators use resistors and capacitors to create the phase shift needed for oscillation. They're simple, cheap, and work well for low frequencies, like audio signals. A common example is the phase shift oscillator, where the signal passes through 3 RC stages, each shifting the phase by 60 degrees, totaling 180 degrees, combined with an inverting amplifier for another 180 degrees. The result, a stable 360-degree loop and a beautiful sine wave output. Second, LC oscillators. LC oscillators use an inductor and a capacitor, and they are absolutely fascinating. When you charge a capacitor and connect it to an inductor, the energy bounces back and forth between them, like a ball bouncing between two walls. This is called a tank circuit. The frequency of oscillation is determined by a simple formula. Frequency F is equal to a 1 upon 2 pi under root LC. Change the inductor or capacitor value, and you change the frequency. LC oscillators are used in radio transmitters and receivers. Every time you tune your car radio, you're adjusting an LC circuit to resonate at your station's exact frequency. Famous LC designs include the Colpitts oscillator and the Hartley oscillator, each named after their inventors, and both still widely used today. Now, what if you need extreme precision? What if your oscillator can't drift even slightly? Like in a GPS receiver or a digital clock. Enter the crystal oscillator. A quartz crystal, when compressed or stretched, produces a tiny electric voltage. And when that voltage is applied back to the crystal, it vibrates at an extraordinarily precise frequency determined by its physical dimensions. This is called the piezoelectric effect. Crystal oscillators are so accurate that a typical watch crystal drifts by less than 1 second per month. Your smartphone's clock, driven by a crystal oscillator, your Wi-Fi, synchronized by one. They are everywhere. By now you might be wondering, where exactly are oscillators used? The answer is almost everywhere electronics exist. Every microprocessor has a clock oscillator. It's the heartbeat that tells the chip when to execute each instruction. A modern CPU running at 3 GHz has an oscillator firing 3 billion times per second. Radio and TV transmitters use oscillators to generate the carrier frequency that broadcasts signals through the air. Your FM radio tuner uses an oscillator to lock onto a specific station. In medicine, oscillators drive the ultrasound machines that let doctors see inside the human body without a single incision. Even the internet depends on oscillators. Fiber optic networks use them to synchronize data transmission at billions of bits per second. Without oscillators, modern civilization as we know it simply would not exist. Now, here's where it gets powerful and a little dangerous. When the oscillator's frequency matches the natural frequency of whatever it's driving, you get resonance. The waves build up huge energy. That's exactly how inverters create clean 50 Hz or 60 Hz AC that matches your home grid. Miss the frequency. Your appliances buzz, overheat, or even get damaged. Engineers use this same principle to make ultra-efficient solar inverters, noise-canceling headphones, and even medical devices. And the best part? Modern oscillators are so precise they lose less than 1 second per year, all from a tiny piece of vibrating crystal powered by DC. If you want to see oscillation in action, here's a simple experiment you can try with a 555 timer IC, one of the most popular chips ever made. Wire the IC in a stable mode with 2 resistors and a capacitor. Connect the output to an LED, power it up, and watch the LED blink. That blinking is a square wave oscillator, toggling on and off at a rate determined by your resistor and capacitor values. Change the capacitor, change the blink rate. It's that simple, and it's the same fundamental principle powering the most advanced electronics on the planet. Oscillators are invisible, but they are everywhere. Every tick of a clock, every note from a speaker, every signal sent by your phone, all of it begins with an oscillator. So the next time your power goes out and the inverter saves the day, or your phone connects to Wi-Fi, or you charge your laptop without it exploding, thank the humble oscillator. It proves once again, the simplest circuits can create the most incredible transformations. DC to AC, steady to pulsing, battery to your entire modern life. If this episode sparked your curiosity, hit that like button. It genuinely helps this channel grow. Subscribe so you don't miss episode 6, and drop a comment below. Which oscillator type did you find most fascinating? The elegant LC tank circuit? The impossibly precise crystal? Let us know. Until next time, keep questioning, keep exploring, and remember, the universe runs on invisible waves.